And finally, in case of this spherical system, we can guess how the differential length term will look like. Obviously, since r is length itself, so we will get a dr directly from it, but since this theta over here is not a length, instead it's an angle, so we will have to convert it into the length that it covers. Conversion, let's say conversion 1, and this phi is another angle, so this will require another conversion named conversion 2, let's say. For the moment, we'll explain these things shortly. Okay, so let's say you want to start your journey at this point over here and end your journey at this point over here. So these 2 points are part of 2 different spheres. That's what you need to understand here. So this is the spherical wall of one sphere, and this is the spherical wall of the other sphere, and this is basically a zoomed in picture of this portion over here. So it's clear from this picture that the blue colored spherical wall has a greater radius compared to the red colored spherical wall. All right, so in order to move from this point to this point, you will have to first move along the AR direction, so in order to move from this point to this point, you have to increase your radius a bit. You have to move from this sphere, this red color sphere, up to the blue color sphere. So that means you will have to travel along the AR direction by a distance equal to dr. Okay, so if we show it over here, you will have to cover a distance equal to dr along the AR direction. All right, by increasing the radius, you have moved from this point over here to this point right now. Then you will have to move along the A theta direction, I mean this direction. Okay, so this direction was the A theta direction, if you recall correctly. And of course, as long as you are staying on this line over here, you are always staying on the same radius. All right, so by moving along the A theta direction and covering an angle equal to d theta, you're basically covering a radius, an arc length equal to r d theta. Okay, so by covering a distance equals to r d theta, you're reaching this point over here. All right, now for the last one, you will have to move along the surface towards the a phi direction to get to the final point. But this is not as straightforward as the previous one, because when you are moving towards the a phi direction, you are not exactly traveling with respect to the same radius that you used in case of a theta. Okay, so this will not simply be rd phi. This will not be like that. Okay, if you recall correctly from the coordinate systems lecture, we defined phi as the angle the projection of one point makes with the positive direction of x-axis, right? But when we are trying to move from this point to this point, we are not exactly projected onto the xy plane yet, right? To determine how much distance is covered when we move along the phi direction, we'll first have to project this line onto the xy plane first. Okay, so if you look at the picture over here, this length will have to be projected onto the xy plane first, and in this picture the projection line is this. Okay, whenever you're projecting any point on this line onto the xy plane, it requires you to take the sine theta component of r, right? So by taking sine theta component of r, you are taking these you're taking the projection of this whole line onto the xy plane. And so basically the effective radius that this arc has is this, okay? And this is not r, this is r sine theta, okay? So if you move along this direction right now towards the phi direction, you're basically covering a distance which is given by the radius times d phi. And what is the radius again in this case? The radius in this case, instead of r, will be r sine theta. Okay, so r sine theta has a unit of length which gets multiplied to the d phi, which is an angle, and together these two make it a length covered. So basically, if you try to figure out the differential length vector from this whole mess over here, this will be given by dl equals to ar dr. That's pretty straightforward. And then a theta r d theta, that's comprehensible as well, but a phi will have a component equals to r sine theta d phi. All right, so r sine theta will be the effective radius of the arc of the projection of the traversing direction along the phi direction. All right, so this will be the differential length in case of a spherical system. Okay, let's look at the differential areas now. Uh, First of all, if we look at the ABCD surface, which is this is obviously a differential area, right? Because this is infinitesimally small and this is just a cutout of a bigger picture, as we saw earlier. So ABCD has the dimensions of r sine theta d phi along AB direction and r d theta along the BD direction. So if you look from here and take it as a rectangular piece, it will have a dimension of r sine theta d phi and r d theta. So the differential area will be r squared sine theta d phi. All right, and if you want to turn it into a vector again, the perpendicular vector to the uh, spherical surface is basically AR, right? Because the radius is always perpendicular to the spherical surface, so it can be called DSR. Similarly, if you look at the PACR surface, then PA has a length of dr and AC has a length of rd theta. If you look at it from this direction, you'll see it as a rectangle with dimensions dr and rd theta. So ds will be given by r d theta, and the perpendicular vector to this surface is the one variable that's left out. So it's basically a phi, and you can use phi as a subscript over here. And finally, if you look at the bottom surface or top surface over there, which is RCDS, then you'll find it has a dimension of dr along this direction and r sine theta phi along this direction. So ds will be r sine theta d phi into dr. Okay, we're talking about the bottom surface over here. Okay, if you want to turn it into the vector, then the perpendicular vector to this bottom surface is directed towards the a theta direction, so it will be a theta, and here the subscript will be theta. So these will be the differential area quantities. And finally, the differential volume will be derived if we just take it as, if we approximate it as a rectangular parallel pipe again, and just multiply these three lengths. So later in this course, when we'll see some examples and mathematical problems, these concepts will eventually seem a lot easier for you. Right now, at this introductory level, this might seem a little haphazard to you, and there's nothing wrong with it. But the thing is, you'll have to combine these videos with the books that I've uploaded to have a better understanding of what is going on over here. This might seem a little hard for you to grasp, but eventually, if you spend a little bit of time and try to visualize what's going on over here, then eventually you will get to the bottom of it. All right, so don't panic, just spend a little more time on these things, because as we move forward into the course, we will be needing all these concepts a lot.